Hi everyone, Mr. Hamilton here. Today we're talking about refraction, and if you look at the picture in front of you, you notice something funny happening with this beam of light that's coming from the left. As it enters this acrylic block, which is basically a fancy word for plastic, it's bending. And then as it exits the acrylic block, it's bending again. And so this was a mystery for a lot of people for a long time. But what happened was that scientists eventually realized that the light was actually slowing down as it entered the different material. So as it goes into the acrylic block, it's going slower than it's going when it travels through air. And so if you look at this and you were actually to draw the normal on each of these, you would see that what's happening is the light is bending towards the normal as it enters into the acrylic block, and then it's going back away from the normal as it's exiting the acrylic block and going back into air. We're going to see why and how that works in this lesson. So light waves, as we just saw from that last example, change speed and direction when traveling from one medium to another. Change speed and direction when traveling from one medium to another. Well, what is a medium? A medium is a substance that transmits light. It could be air, glass, water, plastic. Those are the most common ones, but it could be a whole bunch of other things as well. We could use different liquids, different rubbing alcohol, things like that we'll see as well. Below it says label the diagram that shows the refraction and reflection of light. And so this is basically a review from the last chapter that we did. And we know that if we label this diagram, that this I is the angle of incidence, and R is the angle of reflection. But we're going to have one other thing that we're noticing here, and that is the angle of refraction. What do we mean by that? Well, we mean that this is the angle of incidence, always measured from the normal. Make sure we label that properly. Angle of reflection. But then some of that light, as we saw when it entered from the air to the acrylic block, is going to bend like this. And this angle right here is known as the angle of refraction. Some of the light is going to refract. It's going to bend into the surface. Some of it is going to reflect off of the surface. And so we have these two different angles. With that in mind, let's also label the refracted ray. It's the refracted ray. It's the one that passes through the new material. And this here is the reflected ray. That's the ray that bounces off the surface. And then this down here is the incident ray. And so this might be plastic or glass or something like that, but it's going to have a slower speed of light in that material than in air. So here's the air on the right, and we've got the plastic on the left. All right. Light traveling into a more dense medium, and the plastic is much more dense, obviously, than air. A more dense medium bends toward the normal, slows down. Light traveling into a less dense medium bends away from the normal. As we saw when the light went from the acrylic block at the beginning of this video back into the air, it bent away from the normal. It speeds up. So I'm going to give you a question of a little bit of an analogy and see if you can figure this out for yourself. We've all had the experience, probably at some point in our childhood, of pulling a wagon. And the wagon, the front wheels turn separately from the back wheels. And when you pull that wagon off of the sidewalk onto the grass, you notice that the wheels that hit the grass slow down because the grass is more dense, if you will, than the sidewalk. And so if you do that, what's going to happen? Just stop this video and pause for a second and think which one of these three scenarios plays out when I were to pull my little wagon onto the grass. Now, hopefully you've agreed to think that it's actually A. And maybe a better analogy than grass would be to think about this as mud. And here's why. You're pulling your wagon and you've got all four wheels. Let's just assume these front wheels here aren't there yet, but they're right here and here. And what happens when this front wheel hits this mud? Well, this front wheel slows down. But this one on this side is still going fast. And so this one begins to slow down. The other one's still going fast. The other one makes up time on the other one. And so what happens is this one ends up going here, whereas this one ends up being almost stuck in the mud. And so that axle is going to bend, And that's what you see here, is you see this front axle having bent. And so as you hit the mud, it's going to slow down. So as you hit something that's more dense, it slows down and bends the whole thing towards the normal. Consider this analogy with cars, for example. Consider the one on the right first here. The car has these two wheels. There's the first wheel, there's the second wheel. As those two wheels driving from the pavement into sand, this first wheel is going to hit the sand and slow down. Whereas this other wheel on the other side is going to continue to move quickly, and so eventually that wheel is going to make up space on the other one, and the front axle of the car is going to look something like that. And so it's going to then bend towards the normal. Remember, the normal is this line that's 90 degrees to the surface. And so what we have is, after we've gone to the more dense medium, so the sand is more dense, the pavement is less dense, just in terms of what you're driving on in this case. It's an analogy. It's going to bend towards the normal, and that angle, the angle of refraction, is going to be smaller than the angle of incidence. Now notice on the left here that the car is driving straight into the sand. Well, in that case, it's obviously going to slow down, but because both of the wheels are going to hit the sand at the exact same time, they're going to slow down together, and the car is not able to bend. So if we're coming exactly along the normal, there's going to be no bending, but there will be slowing down still. Only at the angle are we going to see that bending. So going back to the handout, the analogy says, think of it as a shopping cart. We've also thought it as a wagon or a car being pushed from pavement into mud at an angle. Mud is more dense, so the shopping cart, car, or the wagon will turn toward the normal. The angle is going to get smaller to the normal. So that's the key idea here. If you're in the academic class, we're going to now look at the index of refraction. Since light speeds up and slows down as it goes from one material to another, the index of refraction is simply a ratio of the speed of one material to the speed in another material. So let's write down this definition. The index of refraction, and we call this n, the index of refraction, which is known as little n, is the ratio of the speed of light, in a vacuum. So that's through anywhere in space, really, because most of space has no medium, no air, nothing in it, to its speed in a material. So some other material like glass, like plastic, like rubbing alcohol, things like that, and that is going to be labeled as V. N, the ratio, is C divided by V. So it's the speed of light in a vacuum divided by whatever the speed of the material that we're dealing with is. And now, if I was to ask you to find any one of those variables, knowing the other two, they relate in this way. N is equal to C over V. So what we get from this is N is C over V. If we were solving for C, we would get its N times V because they're beside each other. And if we were solving for V, we'd have C over N, and that would be how we'd solve for V. So with that triangle, which you'll be given on any assessments that we need, you can go ahead and rearrange that for anything. You could also just take this equation and rearrange it, but you'll have both this and that triangle to use for this equation. So here's the question I want to ask you. What's the speed of light in flint glass? I'm going to give you one piece of information here. Let's write the question first. What is the speed of light in flint glass? There's many different types of glass, so we're talking specifically here of flint glass. And so the givens that I'll give you, we know that C is 3.00 times 10 to the 8 meters per second. That is the speed of light in a vacuum, and it is always the same. Well, remember, that's in scientific notation. That's the same thing as taking the decimal place and taking it 8 places to the right. So if we were to do that, we would get 300 million meters per second. But we write things in scientific notation now. The other given that I'll give you in this particular case is, if you look at table 11 on page 454, you can find a whole list of all of the all of the index of refractions. And the index of refraction in flint glass is 1.65. And so what we're required to find here is the speed of light in that flint glass. So V in that flint glass is what we're after. Well, how do we rearrange this equation? Well, n equals c over v. That's not in the form we want it, but we have the triangle that shows us how to rearrange this. And in this case, if I'm trying to find v, if I block v out on that triangle, then I have c over n left. And so it's 3.00 times 10 to the 8 meters per second divided by 1.65. Now there are a couple of ways to type this in your calculator. You can look for specifically a button that might say EE or another button that might say 10 to the x. On most calculators, it's one of those two. And so if you write 3.00 and then you write EE 8 or 10 to the x 8, that should on your calculator write 3, and then you should have a little times 10 to the 8. And then if you divide that by 1.65, what you should arrive at is a V of 1.82 times 10 to the 8, or 182 million meters per second. So just so that we can see that, it's 182 million meters per second. So that's, again, the reason we say it's 10 to the 8 is the decimals there, we go 1, 2, 3, 4, 5, 6, 7, 8 right there. So 1.82 times 10 to the 8. And we can conclude, therefore, the speed of light in flint glass is 1.82, we're always going to write this in scientific notation now, times 10 to the 8 meters per second. Let's do one more example in case you're not quite grasping this concept. So here's a second example. It says the speed of light in an unknown substance is 1.838 times 10 to the 8 meters per second. What is the index of refraction? Now remember that is n, and it changes depending on what the material is. And B says based on table 11.1 on page 454, what's the substance or medium used? So the first thing we want to do is identify the givens. In this case, the given values, we know that the speed of the unknown substance is 1.838 times 10 to the 8 meters per second. And we always know, always, that the speed of light in a vacuum is 3 times 10 to the 8 meters per second. This is always the same. So the only thing we don't know that we're required to find here is we're required to find the n value. Well, the next thing I want to do is do a little analysis. And in the analysis, I want to identify what equation I'm going to use. Now, you might remember that it's n equals c over v. Or you might remember the fact that is this triangle. Either one is fine. NCV, and you get the equation from that. But regardless, you end up in this equation in this case because we want to solve for n. So now we go ahead and we get the solution by substituting values in. So we get n equals 3.00 times 10 to the 8 meters per second. And if we divide by 1.838 times 10 to the 8 meters per second, you'll notice that the units of meters per second cancel right out, and that's why n does not have any units on it. So in this case, n ends up being 1.632. Okay, well, we found the index of refraction, so we can conclude, therefore, the index of refraction is 1.632. So now we go to page 454, table 11.1, and we identify, looking at this and say, okay, well, what is it? So let's actually have a look at this table together. So what this table shows us is it shows us all the indexes of refraction. And so we have on the right all the solids at 20 degrees, and we don't have 1.632 there. But this carbon disulfide, we do have 1.632. So what this is likely to be is it's likely to be carbon disulfide at a temperature of 20 degrees Celsius. So for part B, we could conclude, therefore, it must be carbon disulfide, and we could note at 20 degrees Celsius. They're going to change slightly depending on the temperature and how that changes. So we've identified the index of refraction, we've identified what the substance is. If you have any questions, as always, ask for help, and I'm happy to help.